This is the fact file answers for topic 4.4 equilibrium in CA chemistry. So, question 1, 1.1 grams of pentanmonol and 1.2 grams of ethanoic acid were mixed. Equilibrium was established at 298 Kelvin. The equation for that, CH3COOH plus C5H11OH in a reversible reaction produces CH3COO C5H11 plus H2O. Write an expression for the equilibrium constant Kc for this reaction. Well, we're just simply looking at the reactants over the products. So we've got the ester here, CH3COO C5H11 times concentration of water, H2O, over the concentration of the acid, CH3COOH, and the alcohol, C5H11OH. Then it says, at equilibrium, 0.6 grams of ethanoic acid remained. Calculate the value of Kc. So I've just written out the equation here again. And initially we're told in the question up here we have 1.1 grams of pentanmonol and 1.2 grams of the ethanoic acid. So 1.2 grams of the acid, 1.1 grams of the alcohol. Then you need to work out the number of moles here. So just finding the formula mass for each. So it's 60 for the acid and 88 for the alcohol. So 1.2 divided by 60 gives us 0.02 and 0.0125 then for the alcohol. Those are the number of moles at equilibrium. And of course the ester is 0 and water is 0. Then it says in this question, at equilibrium 0.6 grams of ethanoic acid remained. There were 1.2 grams to begin with. So 0.6 is just a half, so that's quite handy. So 0.01 is left. That means the same number of moles of the alcohol will have been used up. So take away 0.01 from here, we get 0.0025, and then it's 1-to-1 ratio, so 0.01 of each of the products is produced. Plug those into the equation. Kc is concentration of the ester times the water divided by the concentration of the alcohol times the acid, so the answer is 4. And there are no units. The reason there are no units is because it's just concentration squared over concentration squared, so it gives us no units. Okay. Number 2, which one of the following represents the units of Kc for the equilibrium shown below? It's just the equation for the Haber process. So looking at this, we have 2 moles of product, so it's concentration squared, and we have 3 moles of the hydrogen and 1 of the nitrogen, so it's concentration squared over concentration to the power of 4. So we get rid of the 2 on the top, and that leaves us with concentration squared on the bottom. So that'll be mole to the minus 2 dm6, which is B. Number 3, this one looks hard, but it's actually pretty easy. So if ammonia and methane are placed in 1 dm cube container and heated to 500 degrees, it's found that 0.1 moles of hydrogen cyanide and 0.3 moles of hydrogen are produced at 1 atmosphere pressure. So we're told 0.2 of ammonia and 0.2 of methane initially, and then 0.1 and 0.3 at equilibrium. Calculate the equilibrium constant Kc for the reaction under these conditions and state its units. So initially we're told 0.2 and 0.2, and we have 0 of the hydrogen cyanide and the hydrogen, and then at equilibrium we're told 0.1 and 0.3, which means we have used 0.1 and 0.1. So plugging that into our equation, we've got, that should be a little 3 there, just hadn't come up when I wrote it. So we've got the concentration of the hydrogen cyanide times the concentration of the hydrogen cubed over the concentration of ammonia times the methane. Plug those values in, 0.1 times 0.3 cubed over 0.1 times 0.1, which gives us 0.27. Then looking at the units would be concentration squared over concentration, which gives us just concentration squared, so mole squared dm to the minus 6. Finally, 1 mole of propanoic acid, 1 mole of methanol, and 2 moles of water were mixed and allowed to reach equilibrium. So I've written down here initially we have 1 mole, 1 mole, and 2 moles, and then at equilibrium 0.5 moles of the methyl propanoate was present. So that means 0.5 of this have been used, 0.5 of this, and another 0.5 of that have been produced. Plugging all of those into the equation, 2.5 times 0.5 over 0.5 times 0.5 gives us 5, which is C.